Okay, so welcome to my YouTube channel. In this video, I'm going to solve a problem on numerical analysis. Okay, so this problem is on systems of equations using numerical method. So we have a question here, says use Gauss elimination with scaled partial pivoting and 3-digit rounding off. Okay, rounding arithmetic to solve the following systems of linear equations, and also have to compare with the actual solutions. Okay, so the solutions are going to get may not be accurate, but they must be close enough to the actual solution which is given. And according to the actual solution, we're given the value of x1 as 1.35, x2 negative 4.68, x3 negative 4.03, and x4 negative 1.66. So we need to make sure that in our solution, we shouldn't deviate much from the actual solutions. Okay, so we get started. So the first thing, when you're given systems of equations, you want to use numerical method to solve is first to present your equations in form of a matrix. Okay, so first I'll write the matrix. So since we have 4 equations here, 4 unknowns, we are going to write a 4x4 matrix. Okay, so the first equation will consist of first row. Okay, so the elements in the first equation will make up the first row. In the second equation, the second row, the fourth row, and so on and so forth. So let's go ahead and write the matrix. Okay, so from the first equation, we have pi as the first element. We have a square root of 2 as the second element. We have -1. We have 1. Okay, and then the second equation of e to the power 1, -1, 1, 2. And then third equation of 1, we have 1, -√3, 1. And then the last equation of -1, -1, 1, -5. Okay, now we also have to include the constants, right? So the constants of 0, 1, 2, 3. Okay, so this matrix of written so far, it's called the confusion matrix. But now we have to include the constants as well. So 0, 1, 2, 3. Okay. So this matrix is called the augmented matrix, so formed here. Okay, so this is an augmented matrix. And I'll separate the confusion matrix from the constants by this line here. Let me just use this font. Okay, so now that's the first step. The next step, we're going to get the scaling factors. The scaling factors, since I taught you to use the partial pivoting method, I have to get the scaling factors from each row of the coefficient matrix. So from this row here, I'll get the scaling factor, okay? The maximum of that. From this row, I also get the scaling factor, the maximum of that, as well as from this row, I'll get the scaling factor, the maximum of that. And finally, from this row again, I'll get the maximum value. Okay, and that maximum just be the absolute value. Don't consider the negative, right? So from row 1, okay, from row 1, I'll get the scaling factor, I'll call it S1. So S1 will be the maximum of the elements in row 1, okay, of the coefficient matrix, of course. So you notice that pi, row 2, -1, +1. The maximum value there is what? Pi. That's the largest value we have. So our S1 will be equal to pi. And then the second row, we have E1, 1, and 2. Remember, don't include these constants, right? So you notice that E is the maximum value, right? Because E is about 2 point something. So E is the maximum value for the second row. So I'll call this S2 is equal to E. Okay, and then in the third row, we have square root of 3 as a maximum value. Just need the absolute of it. Don't consider the sign. So press root 3. And then in the fourth element, of course, you can see that is S4, it's a square root of 5. Okay, so that's the first step. The next step is now to get these scaling factors, okay, and divide all the elements in the first column by their respective scaling factors. And from that, we're going to get the maximum. So from this first column, right, we're going to divide those elements with their scaling factors. So we're going to divide pi as the first element. What's the scaling factor in that row is pi as well. So pi divided by pi. Okay, also go divide by e. Divide by what? E as well, because e is the first element as well as e is the maximum value in that row. And then also divide 1 with its scaling factor, which is what? Square root of 3. And then also divide 1, just need the absolute, right? So forget about the negative. Divide by root 5, okay? So from this, we get the maximum. As you can see, the maximum actually is this guy gives us 1. Also, this one gives us 1, okay? And then the other one, what does it give us? So this one gives us about 0.57, okay? 0.577 to 3 digits. Also, the next one gives us about 0.447, okay? So what's the maximum from this? You can see that maximum is 1. So I have 2 maximum values here. Okay, so the maximum will tell us which rows need to be interchanged. Okay, so since I have 2 maximum values, it means we're going to have 2 options, okay, regarding the rows need to exchange. So let me take you back here. This element here is in the first row, first column, so we call it A11. This is A22. Oh, sorry, second row, first column, A21. Third row, first column, A31. Fourth row, first column, A41. Okay, so those subscript will tell us something. So remember that this maximum value came from dividing A11 over S1. This one came from dividing element in the second row, first column. This one came from dividing an element in the third row, first column, A41. So A11 and A21 gave us the maximum from that division, right? So this subscript here will tell you which rows need to be interchanged. So in this case, you notice that row 1 need to be interchanged with row 1, okay? So it means that you're not doing any change, you're just maintaining the same thing. Or if you want, can you go for this one, row 2 interchanging with row 1. So I would go for the second option, row 2 interchanging with row 1. Okay, so I'm going to interchange those 2 rows. So if I do that, what do I have? So I'm going to get for the matrix. So row 1 becomes row 2, row 2 becomes row 1. Okay, 1, you have 2, we have 1, you have pi, you have row 2, negative 1, 1, 0, and then the last one, you have 1, 1, negative root 2, sorry, 3, 1, 2. Okay, and then here you have negative 1, negative 1, 1, negative root 5, 3. Okay, so this came as a result of interchanging the rows. So the operation here, I'm going to write the operation here. It was the row 1 interchanging with what? Row 2. So that's operation here. You need to show that. Okay, now from that, what do you do the next thing? The next thing we do, just like the way we do in Gauss and elimination, right? Where now we have to identify the pivot. So just we have to reduce this to an initial matrix. So we have to identify the pivot from each row. Okay, so we start the first row, we're going to identify the pivot. And remember that the pivot cannot be a non-zero number. So cannot be a 0 number, should be a non-zero number, isn't it? Okay, so in this case, E will be our pivot element. Okay, so the conditions are that the elements below that pivot element should be made zeros, should be zeros, okay? You end up having zeros there. So I have to make sure that these guys are zeros down here. So what do we do? We're going to find the factors that are going to make those guys to be 0. So we have to do the row operation on those three elements. I mean those three rows. So we're going to do operation on that. So for us to do that operation, we're going to find the factors that are going to make these guys to be zeros. And how to get those factors? I'll call those factors M. Okay. So I need to reduce this element here by to what? To 0. So I need to write the factors for that, right? So that factor, I'll call it M for the second row, first column. M21 will be equal to that element itself, which is what? A21 divided by the row, the element where the pivot is. And this case is what? A11, right? The pivot element, of course. Okay. So what do we get there? So that will be pi divided by E. Okay. So what do we get when divide pi divided by E? I get about 1.16. Okay. And then also the next one I'm going to get is this one here, the element, the factor, sorry. I'll call it M31. And that M31, I'll get it by dividing A31 element over what? A11 as well. And this is by dividing 1 over E. Okay. This will come as a result of dividing 1 over E. And 1 over E, this will be equal to what? Approximately equal to 0.368. Finally, I'll get M41. And this M41 will be as a result of dividing what? A41 over A11, right? And this will be the same as dividing negative 1 over E. And this gives us negative 0.368. Okay, now having found those factors, what do we do? The next thing is now to reduce those elements to 0. So I'm going to write the row operation for each row. So row 2, remember reducing row 2, row 3, and row 4. So row 2 become row 2, those are the operation you write, right? Times M21 times that element in row 1. You're trying to reduce element in row 2. So you're going to multiply by element in row 1. Similarly, row 3 becomes what? Row 3 minus M31 times row 1. Okay, remember that you're using row 1 elements to reduce all the elements in the other rows. Again, row 4 becomes row 4 minus M41 row 1. Okay, so we have to do this each element, isn't it? So let's start with row 2. Okay, so row 2 becomes, what is the row 2 element you're trying to reduce? You're trying to reduce pi, isn't it? Okay, so pi minus 1.16, okay, which is M21 times E, okay. So this should give you approximately equal to 0. If it gives you something about 0.0 or something, just say, okay, it's equal to 0. Okay, that's what you're going to get. Okay, and then the next thing, again, the next element you're going to reduce is this element here, which is row 2, of course, because they're moving along that row. So we're going to reduce row 2. So row 2 becomes what? So row 2 minus 1.16. What element are we using now this time around? We're using this element here is negative 1, okay? Times negative 1. So what does it become here? It becomes about 2.57. So about 2.57, okay? And then next thing, what are you going to get? You're going to get it. The next element is what? Okay, so row 2 becomes, which element are going to reduce here? You're going to reduce negative 1. So negative 1 minus 1.16. And then it times the element in row 1 corresponding to negative 1, which is positive 1. Okay, so when you do that, you're getting about negative 2.16, okay, to 3 digits. And then we continue, row 2 becomes the element, the next element, which is a positive 1. So 1 minus 1.16 times the other element in row 1, which is 2. And if you have to punch that correctly, you're getting about negative 1.32. And then next element, row 2, going to have 0. Okay, because you're here now we have 0, and then minus row M21, which is 1.16 times the element in row 1, just negative 1.16. Okay, so these are the new elements we're going to write in that second row. Okay, now let's look at row 3. So let's do the same operation on row 3. So row 3 becomes what? Row 3, okay. So which element are we talking about now? We're talking about this element now, we've moved. So we're looking at these elements here. So start with 1. So this would be 1 minus its factor, which is what? 0.368, M31. Okay, 0.368 times the element in row 1, which is in this case is E. And this, when you do that, should give you approximately equal to 0. Okay. And then again, row 3 for the next element. The next element again is 1. Okay, so we have 1 minus 0.368. We're using it. Okay, we're using negative 1 there. So you see, negative 1 here. And what does this become? This is approximately equal to 1.37. Okay, 1.37, somewhere there. Okay, and then again, we reduce the next element, which is row 3 becomes, okay, row 3 becomes what? What does it become? Okay, so for next element is negative root 3, isn't it? Okay, negative root 3. Okay, negative root 3 minus 0.368 times the element in the first row, which is 1. And this is approximately equal to, okay, negative 2.10. Okay, negative 2.10. And then row 4. Oh, sorry, it's still row 3. Row 3 for the next element, what does it become? You have 1, right? So we're going to look at 1. So this will be 1 minus 0.368 times the element in the first row, which is 2. And this becomes what? This becomes about 0.264. And then we finally reduce the last element. And the last element is what? 2, right? So 2 minus 0.368 times the element, which is 1 in the first row, okay? Or 1 there. Okay, so this becomes approximately equal to, this is approximately equal to what? 1.63. Okay, so now we go to row 4. So row 4, I'll do it here. So row 4, again, the same operation comes, says row 4 minus M41 times row 1. So row 4 is equal to, so row 4, we start with the first element, which is reducing negative 1 minus negative 0.368 times the element in row 1. This should approximately give you what? 0, okay? And then next, again, reduce the next element. The next element you're trying to reduce is negative 1 minus negative 0.368 times the element in row 1, which is negative 1, and this gives us approximately equal to, okay, approximately equal to negative 1.37. Okay, and then row 4 comes, we are reducing, what are we reducing now? We are reducing positive 1 minus negative 0.368, okay, times the element, which is 1 there, right? And this approximately becomes 1.37. Okay, and then the last element we're trying to reduce from row 4. This is what? Actually, not the last one. We still have one more. Negative 5 minus negative 0.368 times the element in row 1, which is 2. This approximately becomes what? Becomes about a negative 1.5. Okay, and then the last element we're going to reduce in row 4 is, of course, 3. So this 3 minus negative 0.368 times the element in the first row, which is 1. This becomes about approximately equal to 3.37. Okay, so now from this information, we're going now to write a new matrix. So remember that the first row is the one that hasn't changed, or everything else has changed. So this is our new matrix. So E, negative 1, positive 1, you have 2, you have 1, you have 0 here. These will be zeros. Okay, remember we have changed these guys. 0, so 1.37. Sorry, not 1.37. You have 2.57. Next is negative 2.16. Next, negative 1.32. Okay, and then negative 1.16. And then here 1.37. Negative 2.10. 0.264. 1.63. Okay, sorry for that. 1.63. And then here negative 1.37. 1.37. Negative 1.50. 3.37. Okay, so this is what you get as our new matrix. And of course, don't forget separating that line. Okay. Now, the next thing again, we're going to repeat the process. Okay, we're going to repeat the process. Again, we're going to find the what? The maximum. Now we're going to focus on the second column. And which column are we talking about this time around? Remember, we started the 4x4 matrix. Now, main focus will be on the 3x3 matrix. Okay, that's how we reduce it. So main focus will be this. So we have nothing to do with this row anymore. Okay, so our main focus will be on this 3x3 matrix. Say again, we're going to find the maximum. Okay, we're going to find the maximum by using the scaling factors that we got from the first procedure. So what are we going to do here? So let's find the maximum. So we're going to divide all the elements of the first this column by their scaling factors. So let's go ahead and do that. So we're going to find the maximum of this. Remember that the scaling factors don't change. Once we find them from the start, we're going to do the same scaling factors throughout. So scaling factors, the maximum of that, which is 2.57, divided by its scaling factors. Now remember that these rows had swapped at some point here. Okay, so this was row 1. Initially, it was row 1. So it means that even its scaling factors has to move along with it. You don't have to use the scaling factors for row 2, despite it being in row 2. Okay, these guys had swapped at some point. This row and that row had exchanged positions. So I have to use S1. So our S1 was what? Was pi, right? So I have to use pi. And then you have 1.37. This one didn't change. So we had root 3 there as a scaling factor. And then again, 1.37. Remember, we just need the positive value of it, not the sign. You don't need the sign, just need magnitude. Divided by square root of 5. Okay. So we need to find which one is our maximum value here. So if you punch these guys, you're getting approximately values of about 0.818. Okay. 0.791, and then you're getting 0.613. Okay, so this now again will tell you more about which rows need to be interchanged here, right? So you notice that here, this is the code A22. Remember, this is A22. Second row, second column. Third row, second column. Fourth row, second column. So from these guys, this is A22. This is A32. This is the A42. So from this, what was the maximum value? Maximum value came from A22. So from this guy here, so means that row 2 should interchange with row 2. Or in other terms, nothing should interchange, right? No rows should be interchanged. So maintain the same rows. And again, we repeat the process now. I have to find the m's, right? The m's that are going to reduce now, the m's that are going to the factor that are going to reduce the other elements to 0. So here we're trying to reduce these elements. Remember, this now becomes our new pivot. okay, in that 3 by 3 matrix. So to reduce this and this to 0. So I have to find those factors. So I have to find a factors M22. Sorry, not M22, M32, right? Because I have to reduce these two numbers here to 0. A32 equal to the element A32 itself divided by the pivot element, which is A32 in this case. This is our pivot element. Okay, so if we do that, 2.5, sorry, I have 1.37 divided by 2.57. What do you get from this? Okay, what do you get from that? We're getting about what? 0.533, right? So 0.533 the scaling factor. Okay, and then also we have to reduce the scale M42 equal to A42 divided by A22. This is equal to negative 1.37 divided by 2.57. And this gives us about negative 0.533, the same, just different signs. So how to apply row operation just like before. So row 3 now, we're changing row 3 and row 4. So row 3 becomes row 3 minus M what? M32, right? Is it M32? Yes, M32. Now this time around we're using row 2 to change those guys. Similarly, row 4 become M42. So it becomes row 4 minus M42 row 2. Okay, so let's apply quickly the values. So we are trying to change which element. We're trying to change from row 3. We're trying to change 1.37 minus its value is 0.533 times the element, which is 2.57. And if you do this, this should give you approximately equal to 0. Okay, and then row 3 again, the next element you're trying to change is negative 2.10. Okay, which is these guys we're talking about here. Trying to change this, right? Okay, so the next one is negative 2.10. Okay, times the factor, which is 0.533 times the element in the first and in the second row, of course, negative 2.16. And when you do that, what do we get? We're getting about negative 0.949, right? Something like this, approximately negative 0.949. Okay, and then again, next element you're trying to change from row 3 is that element is what? 0.264. Okay, this is 0.264 here. Okay, this one here. 0.264 minus 0.533 times the element in the second row, which is negative 1.32, just the element above it, 1.32, and this gives us approximately equal to 0.968. Okay, and then lastly, we are trying to change the next element from row 3, and that element is what? Okay, so from row 3, we are trying to change this element, which is 1.63 minus 0.533 times the element above, which is negative 1.16, and this is approximately equal to 2.25. Okay, and then we go to row 4. So row 4, remember that you also have to do the same operation. So this is row 4. So the first element we're trying to change from row 4 is negative 1.37 minus negative 0.533. Okay, times the element in row 2, which is 2.57. So this should approximately give you equal to 0. Okay, again, the next element in row 4 we are trying to change is 1.37 minus negative 0.533, and then times negative 2.16. This is approximately equal to, okay, it's giving me about 0.2219. And then from row 4, we have the next element we're going to change is negative 1.50 minus negative 0.533 times the element in the second row, negative 1.32, and this gives me approximately equal to negative 2.20. Okay, and then finally, the element trying to change from row 4, we have 3.37 minus negative 0.533 times what? Negative 1.16. Okay, and this gives me approximately equal to 2.75. Now from this again, we have our new matrix. So remember that the first row is still the same, nothing has changed about it. So I have E, negative 1, 1, 2, 1, and then 0. Also the second row hasn't changed. 2.57, negative 2.16, negative 1.32, negative 1.16. What has changed now is row 3. So 0, 0, this will become 0. You have negative 0.949. You have 0.968. And you have 2.25. Okay, 0, 0. So this row here, 0.2919, negative 2.20, and then you have 2.75. Okay, so this is our new matrix. We're almost there. Okay. We're almost there. The next thing now, again, remember that we started the 4x4 matrix, went to 3x3 matrix. Now we have to focus on this 2x2 matrix here. Okay, this 2x2 matrix here. That's the main focus. We have to reduce now this one also using the same procedure. Okay, so the next thing is to reduce that. Of course, the same scaling factors we used. Okay, we have to scale those and find the maximum in this column now. So this is the column we're talking about. So again, maximum, need to find the maximum of what? The element there. So the maximum of, we're going to divide 0.949 divided by its what? The scaling factor, remember? And what is our scaling factor? Our scaling factor is what? Okay, our scaling factor was what was it? I just forgotten. Square root of 3 in this row 3, right? Square root of 3, and then we're also dividing 0.968 over the scaling factor, and it was root 5 from row 4, right? That was root 5. And then what's the maximum here? These guys just give me about, this one gives me about 0.548. Just give me about 0.097 something there. So you notice that this gives us maximum. And this element, as you can see, this element in third column, third row, right? So this is A33 element is the one that gives us maximum, right? A33. This is what? Fourth row, third column, right? A43. So this one gave us maximum. So no row interchange again, work up. We maintain the same. And of course, mean that now this one becomes our pivot element. So I have to reduce the element below it, right? And which element are we supposed to reduce? We have to reduce this 0.219 to 0. Okay, so we have to find again the same M for this now single row we're trying to reduce. So this row 4 now becomes the operation. Oh, first of all, we get M. So to get M, the M for that element, which is element here, which is M fourth row, third column, M43. This becomes what? The element itself, which is A43 over the element A33, which is a pivot element we have chosen, right? Okay, so A43 is 0.219 divided by negative 0.949. And this gives me approximately equal to negative 0.231. Again, now we reduce that element, isn't it? So let's try to reduce this. When you try to do that, you're going to have row, remember the operation just for row 3, right? So row 4. So row 4 is equal to row 4 minus M43 times, now we're using row 3 to reduce row 4. Okay, so row 4 becomes row 4, which is 0.219 minus negative 0.231 times the element in row 3, which is negative 0.949. And if you do that, this will approximately give you 0. Okay. And then again, the next element to introduce is that negative 2.20. So negative 2.20 minus negative 0.231 times that element, which is a what? Okay. So which element are we using this time around? We're using 0.968 in the third row. 0.968. This gives me approximately equal to, so about negative 1.98. Okay. And then the next element we're trying to introduce from row 4 is 2.75 minus negative 0.231 times the element in row 3, which is 2.25. So this gives approximately equal to 3.27. Okay, so now this is our new matrix. We're going to have our final matrix. And this matrix is called an echelon matrix. Okay, so we have the elements now from row 1. Remember, row 1 still nothing has changed about it. Just negative 1. Okay, we have 1, we have 2, we have 1, right? This becomes is 0. This is 2.57. This is negative 2.16. This is negative 1.32. This is negative 1.16. Okay, this is 0. This is 0. This is negative 0.949. 0.968. Okay, and then 2.25. And then you have 0, 0, 0, and then negative 1.98, 3.27. Okay. So we have reduced the matrix to this actual matrix. So I'll spray this again, a red line. Okay, now having done that, we're going to do what we call backward substitution, right? So this guys here, this will represent x4, this will represent x3, x2, x1, like that. Okay, backward substitution. So we're going to solve starting from the bottom, going to the top. So our first equation will be negative 1.98 times x4 should be equal to 3.27. Okay, so that will be our first equation. Okay, so what do we get from there? So 3.27 divided by negative 1.98. So you're getting about negative 1.651, right? So this approximately x4 is equal to approximately equal to negative 1.65 to 3 digits, right? Okay. Next, we need to find the next one using negative what? So the next element is at negative 0.949. This will be multiplied by x3 plus 0.968. This should be equal to 2.25, right? So I have to solve for x3. X3 just be equal to 2.25. Okay. Or this will be by x4, right? Okay. 2.25 minus 0.968 x4. Okay, this divided by negative 0.949, right? So you substitute the value of x4, which you just found previously. Okay, so you substitute that, you should be able to get x3 to be negative 4.05. Okay, and then the next solution will be from this row here. 2.57 and the rest of the elements. So we have 2.57 x 2, 2.16 x3 minus 1.32 x4. This gives about negative 1.16, and you have to solve for x2, right? Because that's the only value we don't know. So this will be 1 over 2.57 times negative 1.16 plus 1.32 x4 plus 2.16 x3. So all you need just substitute the previous values you found here for x4 and x3, and this should gives you approximately equal to negative 4.70. Okay. Move to the last one, which is x4. So this one I'm going to use make use of the whole equation. Ex4, so ex1 minus x3, x2, sorry, and then plus x3 plus 2x4. This is equal to 1. And then so for x1, so x1 will give you 1 over e, in brackets 1 plus x2 minus x3 minus 2x4. And then again, you substitute the values of x2, x3, and x4 there. They should give you approximately equal to, as x1, 1.34. Okay, 1.34. So now you can go back and compare with the original values that are given there, saying the actual solution. Okay, so the actual solution was 1.35, negative 4.68, negative 4.03, and then negative 1.66. You can see how actually accurate you were, and you haven't deviated much from the true values that are provided there. Okay, so thank you for your time. Thank you for watching. Just stay tuned for more videos that are coming on numerical problems, and also can give suggestions what kind of problems you want me to create, like the content you want me to share with you based on numerical problems as well, and also other engineering mathematics. Thank you so much.